What's up, kids? This is Mr. Carlson. This is C-squared mathematics, and we are going through our last lesson of statistics this week. So we are wrapping up 5.4, sampling distributions. We learned a little bit about the central limit theorem yesterday, but now what we're going to be doing is actually applying the central limit theorem to actual application, mainly probability. So how can I use the sampling distributions, the sample mean, the sample standard deviation, and how it relates to the populations? How can I actually use that information and apply it in probabilistic contexts, probabilistic scenarios? I'm going to show you that during this lesson. We're going to skip bell work. We do have the homework quiz for 5.4a. It's going to be 5 questions. And then go through the objective of the central question. What is it truly that we're trying to learn today? And 5.4b to finish up the week. You have work days for the rest of the time. So homework quiz 5.4a, you do have 5 questions. It is 20 minutes long. Okay, remember this is optional for all students now. So if you want to raise your grade, by all means take it. But if you don't want to raise your grade, or if you don't really have the time, honestly, then don't take it. But regardless, either way, please review your answers afterwards if you do take it, and then send any partial credit requests if necessary. Begin your notes for 5.4b. Remember, the note packets are on Google Classroom. You can feel free to print those off and follow along. Right now, where I'm at is the probability section. Okay, so I'm at the probability section. It's going to be on page 5. So if you printed out the key or the notes, it's going to be page 5, probability section. Let's get started. What are we learning today? We're going to first ask, what is the central limit theorem? We kind of already know what the central limit theorem is. It has 2 properties. The population needs to be normally distributed in order to transfer that to the sample. So the sample is normally distributed. Or if the population isn't normally distributed, this is the second part. If the population isn't normally distributed, that means that the sample must have at least a sample size of 30 or more, so that it can be normally distributed. If neither of those work, then that's going to be next week. I'm going to show you what that is when both of those don't work. But for right now, that's the central limit theorem. What is it? We're going to go more into what it is and how it relates to samples and populations by asking, how can you use it to find probabilities of sample means? How can you use it to find the probabilities of sample means? Okay, let's get started here. Probability in the central limit theorem, what do we have? So in order to transform an x value, so something that is randomly just given to you, like a data set basically, in a random problem, an x data set, to what we call a z-score, to standardize that x value. If I want to standardize this x value to be a standard normal curve, instead of just a normal distribution, but a standard normal curve, I can use the following formula. Okay, so let's write this out. What I'm going to have is z equals, and then I have my value. Okay, actually, do I have this right here? No, I don't. Okay, I'm just checking. Okay, so the value, and then minus my mean. And this is all over my standard error or my standard deviation. Now, this is our normal z-score formula. X minus my mean. This was x minus my mean all over my standard deviation. Now, hold on. Since we're doing samples instead of my population, okay? Since we're doing the samples instead of the population, these are going to change a little bit. How are they going to change? How are these going to change? Well, now they're going to change as such. I'm going to actually have this information. So this is going to be x, just my values, okay, my x values, whatever they are, and then minus my sample standard deviation or sample means all over my sample standard deviation. This will continue to be rewritten as this, which you don't necessarily need to write it on this side because I'm actually going to probably let's do this. This is gonna, well, I'm just gonna do it. This is gonna be rewritten as x minus my population standard deviation, my population mean. Sorry, my population mean all over. What does this equal? Our formula: my population standard deviation divided by the square root of n. Now, here's something that's very interesting. Okay, notice one thing. We were talking about sample means in 5.4a. Okay, sample means. And when we found sample means or values, okay, notice this. When we found sample means or values, we had to dabble and do probability distributions and find the mean of those sample means, and then find the variance of the sample means, the standard deviation of the sample means, and so forth. So we took that mean, x bar, the sample mean, and we performed arithmetic using, we performed arithmetic basically interacting with the population and the standard deviation. So what does that mean? Well, that will equal this, okay? And this is going to be x bar as well, and that's going to be x bar as well. Now, why are these x bars? It's because the values, this is still a value, the values that we're interested in with a sample is not just a random value, but it's really the mean of those values. Because that's what we did in 5.4a. We took the mean of the values that we were calculating, the sample means, and we were interacting with the population, not with random values, but with the mean of the sample. The mean of the sample is this, guys. So the mean of the sample will be x bar. This is your sample mean. So don't get that confused. This is your sample mean. But at the same time, when we interact this sample mean, when we find the mean of this sample mean, it is what we call this, okay? Mu sub x bar. So this is the mean of the sample means, so of the sample means, okay? And sometimes, yes, we just simply call this the sample mean as well. So I know it is confusing with all the lingo, the stats lingo, but this is the formula that we're going to be doing. Just know that we're taking sample means. These values are what we call the sample means, and we're performing arithmetic on them, namely z-scores, finding it standardized, so that we can see how it relates to the population. Okay? So let's go through this example. Let's go through this one example. So the figure at the right, this right here, let me erase some of this stuff. The figure at the right shows the length of time people spend driving each day. You randomly select 50 drivers, ages 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5? Now notice this is what I was driving home at. Get it? Because it's driving. Okay. What is the probability that the mean time? So my values here are actually means. So my values are means, but I'm trying to find probability not just with my population means, but with my sample means. So that's why I'm using x bar. So I want to try to make that very clear. Okay. What am I going to do and how am I going to solve this problem? Well, first of all, I'm going to erase all this, and I'm actually going to split this up. So give me 1 second. Don't you love my little Spotify? Give me 1 second, because I'm actually going to split this up right here. And I'm going to take my stats, and I'm going to put it on this side. And I'm going to make this one a little bit bigger, because I don't need all of that. Perfect. Okay. I am going to be using what we call the normal distribution calculator here again. Okay, I'm going to be utilizing the normal distribution calculator here. So let's put this in purple. Okay, let's put this as, where's the formula? So z will now equal my x bar, so that's x bar, and then minus my population mean or my, sample mean all over the standard deviation of my sample, or the mean of my standard deviation. Okay, the standard deviation of my sample means. Okay, so now what are we to do? When I have something like this, I'm going to use my standard. I'm actually going to make this a little bit bigger. My apologies. I hope it doesn't get too. Is it going to get really upset? Okay, great. Fantastic. Okay. So I want room to work over here on this side. Actually, let's get rid of. No, I'm not going to get rid of. Okay. Sorry, I'm just trying to do all this stuff at once. So now, what do I have? Well, the first thing I have, and this is going to be my first step, guys, I need to know what my sample mean is, or the mean of my sample means. What is that? Well, that's going to equal my population mean. What's my population mean? Well, they say this. The figure at the right shows the length of time people spend driving each day. Okay? So what's the average time? So length of time driving each day, and this is the by group, but this is the average right here. So the average time. So I want to know between 15 to 19. You select 50 drivers, but 15 to 19. So I want this age group, and this is my mean. So if that's my population mean, what's going to be my sample mean? 25. And so that's my first answer, 25. Fantastic. Okay. I also want to find at the same time my sample standard deviation. So this is the formula for that. And of course, we should know that from the last lesson. So what is my population standard deviation? Well, it's 1.5. So I have it right there. So 1.5, I'm going to write that. Okay, and then this is all over radical. What's my n? Well, my n is kind of right here. It's kind of hidden in plain sight. It's 50 drivers. So I'm actually looking at 50 drivers. Now, it doesn't say that my population is normally distributed, right? However, since this is greater than 30, the central limit theorem does apply. And so now I can take that 50 and put it right here. When I do that real quick, 1.5 divided by the square root of 50, I get 0.2121. So this is my standard deviation of my sample means, the standard deviation of my sample means. Fantastic. So now what I'm going to do is going to go to my second step. Okay. My second step is to actually standardize this. How do I standardize it? Now, let's be clear. I don't need to standardize it. Let's be clear there. I don't need to standardize it. I'm going to use my z-score formula, but I do not need to standardize this junk. Why don't I need to standardize this? Because I have Desmos. Okay, I don't need to put a standardized version in here. Look. This is not 0 and 1. My mean and standard deviation already are not 0 and 1. They don't need to be. However, sometimes Math Excel will ask you to give you the z-scores, and you do need to comply and give the z-scores. So what's my z-score formula? My mean. So what's my mean? Well, I'm between 24.7 and 25.5, which means I need to find two separate z-scores because I'm given two separate means or two separate values, which means I have z sub 1. So what's my first value? It's going to be 24.7. So this is 24.7 minus the mean of my sample means, or my population mean, whatever you want. It doesn't matter because they're equal. That's going to be minus 25. And this is all over the standard deviation of my sample means, and that's going to be this. So I'm going to actually do this data right there. So 0.2121. This will approximately equal, when I simplify this, and you can do it right here on the calculator if you want to, but this is approximately going to equal negative 1.41. This is my first z-score. Now, I'm going to show you that you don't need to know this in a little bit, but that's my first z-score. My second z-score, using my second value or my second mean, is going to be 25.5. So I'm going to do 25.5 over here minus 25 is the mean of my sample means, or my population mean. It doesn't matter. It means the same thing. and then all over, again, the standard deviation of my sample mean, which is just that. So 0.2121. What does Z2 equal? When I simplify all this and I plug in the calculator, I get 2.36. This is my second Z-score. That's my second step. Awesome. So now what's my third step? My third step is literally to find the probability, watch this, the probability of negative 1.41, where Z is between that and 2.36. That's really what I'm trying to find. I standardized my means. I standardized my values here. And so since I standardized those values, I am given this. However, watch. Okay. Actually, you know what? Let's find that first. And now I'm gonna show you something. So let's find this first. And now I'm going to show you that this will actually equal another probability. But before I get there, let's simplify this and actually give an answer. So I'm going to, let's erase that junk. Let's go over here. Sorry. All right, so, wow, what is that? Okay, so 25, I am standardizing it. I standardized this graph, right? So since I standardize it, I need to use my standard normal curve, which means my mean has to be 0 and my standard deviation needs to be 1. Okay, that needs to be true. Now, what is my min and what is my max? Well, I found these two things, right? My min is probably the negative 1, so the negative 1.141. My max is the positive 1, my positive z-score, so 2.36. So this right here is my probability. Okay, so my probability does equal 0.9116. I'm going to interpret it in a little bit. Just give me a second. Okay, I'm going to interpret this in a little bit. Just give me 1 second. Now, what we did was we standardized using z-scores. But watch, and we learned this in 5.2, so hopefully you remember. Do you need to standardize the graph? Do you need to standardize the normal curve? No, you do not need to standardize the normal curve. Okay, you don't need to. In fact, you can just keep the normal curve as such. Okay, what does that mean? Since this is greater than 50, I already know that the sample means are going to be normally distributed. Okay, it's just not standardized. It's not a standard normally distributed or a standard normal curve. Okay, so it's not a standardized normally distributed graph. It's just a normally distributed graph based on the central limit theorem because it's greater than 30 degrees or 30 degrees. It's greater than 30. These 50 is greater than 30. All right, now what we did here is we standardized the values and then we plugged it in. But because Desmos is so sophisticated, we don't need to standardize and do 0, 1. And we don't need to plug the z-scores in here, which means we don't even need to find the z-scores if we don't want to. How do you do that, Mr. Carlson? I'll show you. What if we just plug in these values as they are? We don't need to take these values and standardize them like this, right? We don't need to. So let's just plug these values in exactly how they are. So watch. So I'm going to say the probability of x between 24.7 of x, not z, but x, 24, technically this is x bar, my x bar between 24.7 and 25.5. That's really what we're trying to find. So now my z-scores, my standardized graph is here. My just regular non-standardized graph is here. My non-standardized values is here. But watch, it will equal the same thing. So let's go to my actual calculator and type these in. So this is going to be 24.7, and then I want 25.5. Now, you will probably say, this isn't the same thing, Mr. Carlson. Joke's on you. Well, joke's on you because I haven't changed my mean yet. What's my mean? What's my sample mean? My sample mean is 25. That's the mean of my sample means. what's the standard deviation of my sample means? Am I going to use my population standard deviation here, 1.5 minutes, right here on that side? No. Why would I use that? What I want to do instead is utilize the standard deviation of my sample means. Because again, I'm trying to perform this probability on the sample, not the population. We already know how to find the probability of the population. We did that in 5.2. But now what we're going to be doing is find the probability of the sample, not the population, which means I'm not going to use the population standard deviation. I'm going to be utilizing the standard deviation of my sample, or the standard deviation of my sample means, which we found is this, 0.2121. So I'm going to erase this, 0.2121. Now, it's a little bit different. Let's do that. Yeah, it's a little bit different, and you'll see where it's a little bit different. Okay, so what we originally got was 0.9116, and this one is 0.91217. Now, watch if we actually change this. What if we actually change this to be just 1.5 divided by, watch, the square root of, let's just say, 50. Okay? Notice how it's a little bit better. So if we actually type that whole thing in, that whole formula in there, it's a little bit better, but still a little bit off. Now, which one's more accurate? To be honest, it's this one. Okay, it's this one that's more accurate because you don't lose as much rounding in there. The reason why you lose a lot of things when you actually plug this in is because this is rounded. So you rounded your you rounded the standard deviation of your sample means. You plug that rounded answer in for your z-score, so you got another rounded answer within a rounded answer, namely your z-scores. And because those are rounded, when you plug those in, you get something that's not necessarily accurate. However, when you use the accurate data, like such as this, with the formula and it calculates it for you, and the actual mean values that they give you in the problem, and not standardized like what we did here, this is the most accurate that you can get. Okay? So from here on out, I will more than likely do it like this, where I won't necessarily standardize it for you. However, because Math Excel wants you to find the z-scores, whenever they ask you find the z-scores, I will be finding the z-scores, but I won't be utilizing the z-scores to plug it into Desmos. I hope that's clear. If the question asks us to find the z-scores, then I will find the z-scores, but I won't be utilizing the z-scores to plug them in to Desmos to find my probability. Okay? I will be utilizing the actual means or the actual values that they give us in the problem, such as 24.7, 25.5, and utilizing my mean of the samples and the sample means, and then the standard deviation of the sample means in order to find the question, not 0, 1 standardized. Does that make sense? I hope. Probably. Okay, so now what is this? Let's just go, because we boxed this. It looks all nice. Let's just go here. What does this actually mean? Okay, what is this? How do I interpret this? Okay, so what this means is of samples of 50 drivers. So of samples of 50 drivers, because I have 50 drivers here. So of the sample of 50 drivers, approximately 91.16 or 91.2%. Okay, about 90, because I'm putting it as percent, this is about 91.2%. Out of 50 drivers, ages 15 to 19, about 91.2% have a mean, driving time between 24.7 and 25.5. Okay, about 24.7 and 25.5. That's what it means. So out of 50 drivers between this age group, about 91.2% have a mean driving spending time of 24.7 to 25.5 minutes. So roughly about 30 minutes, right? probably to go to school and back. Okay, I hope that makes sense. Now we're utilizing what we did in 5.2 when we found probabilities using the population. Now we're just utilizing that. We're utilizing the exact same math, but using it with the sample instead of the population. So let's erase all this and let's move on. Okay, I'm going to go a lot faster with these questions. Okay, I'm going to go a lot faster with these questions. So with this question, what it's asking us is a lot of different things. First of all, it's going to give us a different n. So now you randomly select n drivers, 100 drivers. So I'm actually going to go off to the side. My n equals 100 between 15 to 19, just like our last example. Okay, that's cool. What is the probability that the mean time they spend driving each day is between also 24.7 and 25.5 minutes? So it's the exact same thing, right? And we're going to assume that my population mean is 25, and then my standard deviation of my population is 1.5. Now let's write out my sample mean and my sample standard deviation from the last slide. So my sample mean was this. 25, it's going to be the exact same thing. Okay, was that like, yeah, yes, it was. Great. And now what's going to change is this. This is what's going to change, and this is my first step. Actually, let's call this A, because I guess they say, A. So it says use the central limit theorem for A. Use the central limit theorem to find my mu sub x. This should be right here, my mu x bar, and then right here should be my standard deviation x bar. To find those and sketch the sampling distribution of the sample means. I'm actually not going to show you that. It's just go back. It's really what we did for 5.4a. So I'm not going to show you that. Very simple. It really is just a normal distribution with the mean in the middle. Now I'm going to go to find the z-scores. So actually, let's go there. Now, since they're asking us find the z-scores, we are going to find the z-scores. But before I even do that, I want to find my standard deviation, my sample standard deviation. What the junk is that? What is my sample standard deviation? Well, since my n is going to change, this is going to change, right? So I really need to find that. Okay, so what is that? That is going to be my population standard deviation all over radical n. My population standard deviation is still 1.5, and then my new radical n is radical 100. So this will actually equal 0.15. So a lot nice and crisp. So I need to know that, my sample standard deviation. I need to know my sample population, my sample mean, and I also need to know my n value. So now, since we know that, we can go to B. If you want to call this A, technically I guess it's A. We just don't have the graph for it, and I'm not going to do the graph. But B, let's go to B. Find the z-scores. I do need to have two z-scores because these are my x values. These are technically my x bars. Okay, those are my x bars. And what I have now is going to be exactly what I had before, but just a little bit different. And the reason why it's going to be a little bit different is because I have a new standard deviation of my sample, right? So I have 24.7 minus 25, just like before. But now instead of dividing 0.2121 with a sample size of 50, we're going to do a sample size of 100. So that means since I have a sample size of 100, I get a different sample standard deviation, which means I need to plug that right here. So when I calculate that out, I actually get negative 2.00. So this is my first z-score. Again, I'm not going to use this z-score and plug it in here. I'm going to use my actual mean value data. It's like 24.7. I'm going to actually use that data here. I'm not going to use my z-scores. I'm finding my z-scores because they're asking me to. And then I want to find my z sub 2. So that's going to be 25.5 minus 25 all over 1. Whoops, I'm going to erase that. 0.15. So 0.15. Again, just like that. When I do this, my second z-score is going to be 3.33. So that is my second z-score. Again, they just wanted us to find it. That's all. Okay, fantastic. Now, what is C? Now that I found my z-scores, let's go to C. Let's do this in red so it's a little bit different. Because it's going to be, I need it to be very standing out. Now, I could find the probability between negative 2.00 of my z-scores and 3.33. I could change that to 0. I could change that to 1 and then put in my z-scores right there. I could absolutely do that. I'm not going to, though. However, I am going to do this, find the probability of my x values, my means, being between 24.7 and 25.5. That's what I'm actually trying to find. Okay, so what is that value? Well, let's go to Desmos to find out. Okay, I already have this mean set up. That's already 25. That doesn't need to change. This is solid, but I do need to change this. And then I find my min and my max being the exact same thing. So really the only thing I need to change is that. So that means it's just going to be 100. And that is my answer. So about 0.9768. So I'm going to write that right here. So 0.9768. So this is my probability. D, interpret the results because we need to interpret it. I'm just going to speak it. I hope that's okay. Interpret it. Of the 100 drivers, approximately 97.7%, because that's going to round to a 7, the 8 rounds to 6 to a 7, about 97.7% of those drivers, of those 100 drivers, of 15 to 19 years of age, have a mean driving time of 24.7 to 25.5 minutes. So of those 100 drivers, about 97.7% have a mean driving time of 24.7 to 25.5 minutes. That's the interpretation. Sweet. Okay, so we did that question. Now we're going to go to town. All right, I'm probably still going to show you some of the z-scores here and there, but again, if they don't show you the z-score, if they don't ask for the z-scores, I'm not doing it. Okay, let's erase this. So mean room, the mean room and board of the mean room and board expense. I was like, the mean room? It's really that angry. The mean room and board and expense per year at a 4-year college, at 4-year colleges is $7,540. That's like super cheap. You randomly select 9 4-year colleges. So automatically what I have over here is my n equals 9. Okay, my n equals 9. Perfect. Okay, and then my mu, let's actually get that too. My mu, my population mean is going to be 7,540. Awesome. So what is the probability that the mean room and board is less than 700 or 7,800, 7,800? Now assume that the room and board are normally distributed. Now this is important because n is less than 30. So if the population isn't normally distributed, then we're stuck. But since the population is normally distributed, this does not need to be greater than 30, as per the central limit theorem. And that the population standard deviation is 1,245. So I'm going to write that. So 1,245. Perfect. So these are all my variables listed out. Let's start to find a couple of things here. Okay, first of all, I want to find my sample mean. That's going to be equal to my population mean, which is just going to be 7,540. Done. Okay, I also want to find my sample standard deviation, or my standard deviation of the sample means. This is equal to the population mean all over the square root of n, my sample size. What is that? Well, my population standard deviation is 1,240 all over the square root of my sample size, which we said the sample size was 9. When I simplify this out, I actually get 415. Okay. My second step is going to now be to find the probability where x, my sample mean, is less than 7,800. Is less than 7,800. I could find the z-score over here. So z equals 7,800 minus my population, a mean, 7,540, all over the standard deviation of my sample, so 415. I could find that out, and what I would find is this, okay? But I'm not going to use that. So I could say the probability of z is less than 0.63 instead of the probability of my sample mean being less than 7,800. I'm going to stick with this. So what does this equal? This is kind of a bonus. It's not asking for my z-score, so I don't want to find my z-score. So what does this equal? Let's go to Desmos to find out. I'm going to erase some of this. What is my mean, my sample mean? My sample mean is 7,540. I'm going to erase this stuff right here. And what did I find for my sample standard deviation? I found 415. Now I do need to change these mins and maxes. Now what will be my min and what would be my max? So if this is less than 7,800, what's going to be my max? 7,800, right? I don't want to go above 7,800. So that right here is my answer. So I'm going to write this over here. So 0.7345. So roughly 73.45%. So what's the interpretation here? So of nine colleges, approximately 73.5% have an average tuition that is less than 7,800. So an average tuition that is less than 7,800, or a mean room and board that is less than 7,800. That's the interpretation there. Fantastic. Let's erase and let's just start canceling these out. Okay, and that's what it looks like. Yay. And honestly, you could do this too, by the way. You could show this. I just never do because I use it to write, but you could actually click on that and you see that's the exact same thing, which is great. Okay, let's go through example 5.2. This is going to ask us all this fun jazz, which is fantastic, right? And so that means I'm going to scroll over here. Oh, geez. Let's do that. Okay, fantastic. I'm going to scroll over there. Sorry. I'm going to scroll over here and start doing this. All right, so A. What is A going to be? Now, A is just going to say use the central limit theorem and then find your sample standard deviation and your sample mean. Again, this should be your sample mean and then your sample standard deviation, and then sketch the sampling distribution. I'm not going to sketch it here, but I'm going to find that. So what's A? So what is this? Well, this is going to equal your population mean, right? What's your population mean? Let's read. The average sale price is this for a single family house. That's definitely gone up in the last decade, I'm telling you. Okay, so 176,800. Okay, so that's my population mean, my sample mean. What's my sample standard deviation? It is this formula right here. What's my n? My n is 12, so I randomly select this. This is a problem because it needs to be greater than 30. It's not, so we need to make sure the population is normally distributed. So let's read on. And then the standard deviation, I look at the problem, it's 50,000. So I'm going to write that. So that means what I have is 50,000 all over radical 12. What does this actually equal? When I perform this, it actually equals 14,433.76. So 14,443.76. Now, all of this is useless if I don't actually have fulfilled the central limit theorem. So let's read. What is the probability that the mean sales sales price is more than $160,000. Assume that the sales price is normally distributed. All right, so since it's normally distributed, my CTL, my CLT, my central limit theorem is in fact secure. So my population is normally distributed, which means my samples will be normally distributed. I don't need an n greater than 30, and I don't. It's 12. So let's now go to B. I want to find the z-scores. Now, since it only says more than 160,000, I'm only really interested in this. So I'm really interested in the probability of x, my mean, my x bar, being greater than $160,000, which means I'm really only interested in that value, which means I only need to find one z-score. So my z-score here is 160,000 because that's my mean, that's my data value, minus my population mean or my sample mean. They mean the exact same thing. 176,000 all over 800, and then all over what I just found for my standard deviation of the sample, which is 14,433. I know these are big numbers. 0.76. So what's my z-score? When I plug all that in, I actually just get negative 1.16. Kind of anticlimactic. Okay, that's my z-score. I'm not going to use a z-score to find this though. Okay, I'm not going to use a z-score to find that. So C now is going to be finding the cumulative area or the probability that corresponds to each z-score. Now it says to correspond to each z-score, I'm just going to go through each x, okay, each x value, and calculate the probability of the mean sales as more than that. So that's really what we're calculating. So I'm going to calculate the probability of x being greater than 160,000. This will also equal the probability of my z being greater than negative 1.16 if I wanted to standardize it and solve it that way. So now let's start plugging this stuff in. What's my population mean? 176,800. And then I'm going to erase this, my standard deviation, 14433.76. And then greater than, I want greater than 160,000. So, and I'm going to use this one because I don't use my z-score. It's not standardized. I can only use it if it's 0 and 1 here. I can only use my z-score if it's 0 and 1. Since I'm not using my z-score and since I'm not using it as 0 and 1, I'm going to use 160,000. If it's greater than 160,000, that will tell me it's my min. If I tell you I want at least 160,000 and I'm greater than that, that means it needs to be the minimum that you can give me 160,000. So I'm going to put this in as such. And that is my probability. So 0.877 and then 8. So 87.78%. Perfect. D, interpret results. Are you ready? Of samples of the samples of 12 single-family houses, approximately 87.78% of them have an average sales price of more than $160,000. So about 87% of them have an average of $160,000 or more. Okay, that's the interpreted results. Fantastic. Let's erase and move on to the other ones. Okay. So this one, it doesn't need to find a z-score, and we're not going to find the z-scores for this. This is 1. So what is the probability that this randomly selected undergraduate is a credit card holder and has a credit card balance? Who is a credit card holder has a credit card balance of less than $2,700. So what will this actually entail here? Well, let's read and let's try to get some of these data values. It is normally distributed. That's awesome. Okay, definitely normally distributed. I love that. But what's the mean? Okay, so it says a mean, the population mean is right here. So let's write that. So 3,173. And then my population standard deviation is 1120. So my first step really is to just find my Oh, wow, you don't need to even find the samples. Okay, great. Yeah, awesome. Yeah, you don't need to find the sample standard deviation or the sample mean at all. So notice here, guys, it's not asking you anything about the means, right? When it asks you about the means, then you would have to find the sample standard deviation, the sample mean. Since it hasn't and it doesn't, this is actually just a 5.2 question from finding value or finding probabilities, right? From normal distributions. This is exactly just a straight up normally distributed problem. So what is the probability that a randomly selected undergraduate has a credit card balance of X is less than 2,700? Now notice this isn't a mean, it's an actual value now. This is going to be equal to the probability of a z-score less than something. Now, what is that z-score? Let's try to find the z-score just in case. I mean, this z-score formula, since now it's going to be the population and not the sample, I'm going to be utilizing the population z-score formula, and it's this. So my x is 2,700, and then minus, it's going to be 3,173 for my population all over 1,120. And so what that will equal when I do it all together is negative 0.42. This is my z-score, and I could put it right here. I'm not going to put it in Desmos, though. What I'm going to put in Desmos is this. So less than 2,700. Let's go to town on that. So let's erase this. Before I do, even the last example, we could have seen this. So that's 87%. That's a really big chunk, right? That's a huge chunk. And so it's just remember, you can always just click on this and then zoom, and they'll take you right there, and it'll actually give you a nice little graph for it whenever it asks. Awesome. Population, 3,173. What is my standard deviation of the population? Standard deviation of the population, 1,120. And then I want less than. So I want less than 2,700. I'm not going to use this because I didn't standardize my graph. It's not 0 and 1. So let's do less than 2,700. I need to make sure that's my max, right? Because I want it less than. And when in doubt, you don't know, just see, is this less than? Because this value right here, down here, this value, that is 2,700. And is that less than 2,700? It is. So we're doing it correctly. So what's my probability? Right here. So this is 0.336. And then I think that rounds to a 4. Awesome. The probability that the card holder has a balance less than 2,700 is roughly 33.6%. Now, this is 5.2. This has nothing to do with this lesson because this is actually review, and so I totally forgot about that. I put it in here. That's great. However, we are going to go through the samples in the next slide. So what if we continue? What if we continue this and now we say you randomly select 25 undergraduates who are credit card holders? What is the probability that their mean credit? So now you're thinking samples. So this one right here is the populations. This was just 5.2. This right here is the samples. So now we're thinking about sample. And that is today's lesson, 5.4b. Okay, because they introduced the mean. So now I have to do everything all over again. So what is my sample mean? My sample mean is equal to the population mean, which is 3,173. My standard deviation of the sample means is going to be my population's standard deviation, so 1,120, all over the square root of my n. Well, I'm selecting 25 here. I'm selecting 25 specifically. Notice how this first one, in 5.2, it didn't tell us a sample size because I didn't care about the sample. I only cared about the population. But now that I care about a sample, the sample size is indeed necessary. So now I'm going to do 25. When I simplify this out, I actually get I get 224. I apologize, 224. Okay, so I'm going to utilize this information. In fact, I'm actually going to go over here and adjust these values as such. These are my population values, right? I don't want my population values. I want my sample values. So let's adjust it. That's going to be the same thing, but let's adjust this, 224. Now it's going to probably, Math Excel is more than likely going to ask you for your z-score. You don't need to find your z-score, but let's just find it anyways. Again, my z-score formula is going to, for my samples, is x bar minus my mu of x bar all over my standard deviation of x bar. This equals 2,700 because that's my mean. Okay, this is the means. This is a mean. It's my x value minus the population mean or the sample mean, same thing, 3,170. And then all over this, well, this was just 224. Okay, what does that equal? This actually equals negative 2.11. Okay, so now when it's asking us, find the probability, because that's what it's actually asking us, and this is my third step. What's the probability? Okay, what's the probability of their mean credit less than, so their mean credit less than $2,700. This also equals the probability of my z-score being less than 2.11. What does this overall equal? I'm not going to do my z-score here, but I am going to change this. Okay. Actually, no, I don't need to change. It's all done. Yay. Let's zoom in though. I could change this to 0 and 1 to standardize it. I'm not going to, but here I already had it from the last slide, which is great. The last example is 6.1. Awesome. I don't need to change it. It's still less than 270. I can see it on the graph. So what's my actual answer? Well, since I changed my standard deviation on my sample means here, my actual answer is this. So 0.01 and then 7. And then let's round that 3 to a 4. So let's do 4 decimal places. What does this mean, guys? This means, okay, this means that of 25 undergraduates, approximately 1%, almost 2%, approximately 2% of these undergraduates have an average of average credit card balance of less than 2,700. So that's actually really good, right? So your average college graduate has an less than $2,700 on their credit card. That's really good, I think. And when I had a credit card when I was an undergraduate, I didn't have that much on the credit card. So yeah, I was part of that statistic. Okay. Now notice though that this, again, I just want to emphasize that one here, this right here was asked to find a population, and this is asked to find the probability of the sample mean. Okay, and that corresponds to either your z-scores or it corresponds to your sample z-scores or corresponds to your sample means. Okay, now if I erase this, what it's going to ask afterwards is just compare the two examples. So I'm going to verbally speak it as we wrap up here. Okay, I'm going to verbally speak it as we wrap up. I hope that's okay. Okay. Although 34% chance balance less than 2,700, there's a 34% chance of a balance less than 2,700. Okay, and that was in example 6.1. There's 34%. So although the population has a roughly 34% of a chance of a balance, less than 2,700, there is a 2% chance, and that was example 6.2, a 2% chance that the mean of a sample of 25 undergrads will have a balance of less than 2,700. So since it's less than 5%, that's an unusual event for an undergrad to have an average undergrad to have a credit card balance of $2,700, even less than $2,700. Okay? Fantastic. I know this was a long ride, so thank you for sticking with me. I appreciate it. You guys are amazing. So, what did we learn? We learned how to apply the central limit theorem, how to take the population and the sample mean and the standard deviations and apply it together to find probability of a sample mean. And that's really all we did. So that's great. This is the last lesson of this week. The next couple days are going to be work days, so be sure to use the time wisely. Until next time, guys, I'll catch you later. This is C Squared Mathematics. Be sure to like and subscribe.